So the next speaker is also coming from a very, very, very known company called NVIDIA. So those of you which are, I'm sure everybody here in the audience know about NVIDIA. So let me introduce Professor Gal Chechik from Bar-Ilan University, Senior Director of AI in NVIDIA. So Professor Gal, the stage is for you. Come.
Hi, everyone. Let's see that this works. Yes. Okay. I'm Gal Chechik. I'm a professor of computer science at Bar-Ilan University. I also lead the NVIDIA research in Israel. And I want today to focus not on NVIDIA thing, but to tell you about research that we've been doing in the past year or so in the context of visual generative AI and specifically text to images. So I'm sure by now each one of you have seen these amazing, there's technology that allows you to generate images from text, and these models do really fantastic things. But there are a lot of things where they fail, and here are just a few concrete examples. For example, if you ask a model to draw for you a yellow flamingo and a pink sunflower, it just mixes that and gives you a pink flamingo. If you ask the model to generate Snow White and the 7 dwarves, it will just give you tons of dwarves all around. It doesn't know how to count. If you ask to generate some not common objects like a payphone, telephone tziburi, it gets confused and generates something else. And if you want to generate another image of the same character that you already generated, you have no good way to do that. So there's a lot of limitations to these current models. And the common way that the technology currently solves that is by collecting more and more data and training larger and larger models. And the point I'd like to make is that, you know, if I'm asking you an easy question, let's say I ask you, what color is this, or what is this furniture? You spit the answer immediately, right? You know it's a chair. But if I'm going to ask you a hard question, like how do you teach this model to count, you're going to need to think. Because you don't know the answer immediately. It's not very similar to something you already have seen. So we want to teach these models to think. And when we say to think, this means to compute. So it turns out there's this series of new learning problems that are not just training or inference, but actually involve something more complicated. So these problems, they're not just training, because we're going to seek answers to specific questions or specific queries. And they're not just simple inference, because you need to do some non-trivial optimization during training, during responsing, right, during inference. And so this has been done somewhat in language models, and I'm going to show you a few examples of how you can do that in text-to-image diffusion models. So I want to tell you just quickly how this technology of diffusion model works. The idea is actually very simple. You start with an image of, let's say, this kitty. You know, it's a kitten. And now you add some noise, just per pixel noise, additive Gaussian noise, and you add more and more and more noise. And at some point, the noise overwhelms the data, and you just are left with just noise. And now the point is that you use that to train a model that learns to remove noise. So you give it as input a noisy image, and you expect as output a slightly less noisy image, together with the prompt a photo of a cat. So now you repeat that many times, and after you have this model, you can now start with a completely noisy thing on the right side and just denoise, 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 denoise until you get a photo of a kitten. And every time you sample a new noise, you will get a different kitty. That's the basic idea. Let me mention that, you know, I'm going to dive slightly into details here because it's a research I view that as more as a research conference. I want to highlight that the major advances in this area are due to things called latent diffusion models. And here you don't do all this noising and denoising at pixel space, but on some latent representation that you learn. And there are also two important components in these models that any type of technology will probably need to have. The first one is called cross-attention. Basically, for every pixel image, you decide which words in the sentence you're going to attend to. And this is how you basically connect or communicate the text and the image. The other component is called self-attention. And this is for every pixel in the image, you decide which other pixel it should attend to. And this is important because if you want to generate an object that is coherent, you want all the pixels to communicate so the appearance is consistent. So let me go quickly into some of these examples I told you, and I want to show you how this idea of test time computation can solve a lot of these problems. So the first problem is, again, let's say I'm asking to generate a yellow flamingo. And the problem is that these models, when they were trained, they've seen flamingos that are pink, right? They've never seen yellow flamingos. So it's actually their prior knowledge about color of flamingos overwhelm what they're trying to do, and they just ignore what you ask them to do. So how do you solve that? And there are a lot of examples of these problems, and this is our work, how we fix that, and you can see the flamingo is indeed yellow. And how can you do that? Well, the idea is actually pretty simple. The first idea is that you can parse, because you have good language understanding tools, you can take the prompt and connect nouns with their modifiers, right? In this example, you have a red crown and a golden strawberry. You know that the crown is connected to red. And now, and this is actually inspired by a paper from Tel Aviv University here called Attend and Excite. The idea, remember I told you that you produce images by denoising, denoising, denoising. What we do is that we interject a step that is going to force the crown to be red. And the way we do it, we use this cross-attention component that I told you. And we basically want all pixels in the image that are crown, that correspond to crown, to overlap with those that are red. So you denoise and overlap, denoise and overlap, and you repeat that, and in the end, you get red crown and a golden strawberry. And in fact, if you follow from left to right, this is the denoising process, and I'm showing for every word, red, crown, golden, strawberry, this attention map over the image, and you can see that they start with just, right, all words correspond to kind of the same thing, but as this process progresses, red and crown become overlapping, right, in the third column from the left, and golden strawberry, and then you just turn off this new component and you just generate the image as usual. So this works actually really well in tons of examples, and we did a very systematic, long systematic evaluations, and people report this is, by far better than other approaches, with about like double the accuracy compared to baselines. Let me switch to the second problem I want to tell you about, using the same idea of non-trivial computation. If you take these models and ask them to generate something common, like this gift or a Jeep, they're pretty good at generating these. But if you ask them to generate something that is very uncommon, they just either generate something else or generate something weird. The famous problem with hands, they generate a lot of fingers all around. Or an oxygen mask, it just generates something weird. Now, why would you like so much to generate rare objects? It turns out it's important because you can use generative models to help with models that do image understanding. For example, people are really good at imagining things. If I tell you imagine another chair here, it's going to be really easy for you to do that. And one hypothesis is that we can imagine new things because it helps us recognize them later, right? So even if we didn't see something in reality, we can recognize it because we can imagine it. So how can we make these models generate rare concepts or generate images from rare concepts? So we did an experiment, the following experiment. We took 1,000 classes for which we have a good classifier from ImageNet, and we sort them here by how often these concepts appear in the training set. And it turns out that if a concept appeared less than 10,000 times in the training set of the diffusion model, it was already not generating them well. And 10,000 is a lot of examples. So this suggests that perhaps these models, they actually know how to generate these concepts, but you need to help them to do that. And the idea is that this diffusion model, it takes this latent random vector and a prompt, payphone, and perhaps it can generate a payphone only if you give it the right seed, the right random noise. So how do you find these? The idea is that you have a few samples of payphones, of images of the rare concept that you want, and you go back into the space and find those seeds that generate these images, and now you can sample around them and generate new images. So you go back from the data to the noise, find areas in this space, and then you can generate more images of the rare concepts. And this is actually very effective, and it helps you. Just a few examples. On the top left, you see these 3 images of this yellow bird. If you take standard models, you get the ones on the center. You see they're really very different birds. But on the right, examples from our model. So you can really generate new images with new poses, new combinations for those rare concepts. From this, and again, this is from the same model. We did not retrain the model, right? We didn't touch any weights of the model. We can just make it do things that it didn't know it can do. Also for hands. And again, this really helps in downstream long-tail classification and classification of rare concepts. So a third problem. Imagine that you generate an image, and now you want to generate, and you like the character, and you want to generate more images of the same character. Or perhaps in the first place, you want to tell a story, so you want to generate several images of the same character. And this is often this is something people want to do. And today, you don't have a good way to do that. Here's our method. These are results from our paper. The idea here is that you do 2 things. You describe the character first. Like on the left, you see a photo of an old man wearing a hat. And here, it's important that you're going to keep the same man and the same hat. And now you can generate that character in several different images, right? Walking in the park, writing numbers on the blackboard, maybe it's a math professor, but then, eating dinner in a restaurant. And this is consistent. It keeps the same character in very different situations. A few other examples, you can have it in different styles. You can keep consistent. You see headphones and cat in multiple images. And you can basically now generate a story with consistent characters. How do you do that? The idea is, again, no retraining. Just during generation, you generate several images. And remember, I told you about the self-attention component that makes pixel attend to other pixel of the same object. Now we make them attend the same object in a different image. So we keep attention of the same character, of pixel of the same character, across different images. It's also important that you generate variability, right? You don't want the same pose. You can generate different poses in different background, different combination, but of the same character. And you can control it with ControlNet, and systematic evaluation showed that this works very well. A few more examples you can probably recognize, right? An old story illustration of a young girl wearing a red hood. And you can actually now illustrate. If you have a book or a story, you can illustrate it with a consistent illustration. So finally, I'm not going to show the result. This is a paper that we just submitted. Imagine you want to make this model count correctly. And actually, counting is a hard problem because in order to count something, you need the capacity to identify individual instances. And it's really not clear that this diffusion model can do that, but we show that they can. So when you ask for Snow White and the 7 Dwarves, you actually get 7 dwarves, or Goldilocks and the 3 bears. You're going to get 3 bears. So I tried to tell you about this idea of taking pre-trained models and not just feeding them with more data and more compute, but doing post-training thinking to a given query what I'm showing you is that even with text-to-image models, we can teach these models to do very different things that they were not trained for. And thanks to a lot of collaborators at Bar-Ilan, Technion, Tel Aviv University, NVIDIA, of course. And let me just give you a quick riddle in the meantime. This is a perfectly reasonable hand, and you could try and guess the prompt that was used to generate this image. Are we taking questions?
Yes.
Okay, so in the meantime, you can work on guessing that.
Okay. Thank you very much, Professor Chechik. We need you here still. We want to ask you questions. I think that someone is asking about your stock exchange, but no, we will not discuss this now. Later, tell me privately.
I'll be happy to answer questions about research.
Yes, exactly. We will talk about your AI, not about the stock exchange of NVIDIA. Okay. Question? Someone raised the hand there, please.
Thank you. My name is Slava, and I want to ask you, there is a news that with the help of NVIDIA, in Israel, it's being opened a new quantum computing center to run in hybrid mode with supercomputers. And my question is, what are the plans of NVIDIA of doing research in this quantum computing center, and especially in maybe area of quantum AI?
I'm not sure I got the question. I understand the question is about quantum computing center.
Yes, quantum computing center. What will be going on there? What are the plans of NVIDIA in terms of research in the area of quantum AI?
Right. So one thing that NVIDIA already does is allow classical simulation of quantum computers, right? Because quantum computing is very expensive, it's hard to get access to. So one thing you could do in order to accelerate development of quantum computing is that you can simulate some quantum computing on classical computers and on accelerated computing like GPUs, right? And so today, NVIDIA has a lot of tools to allow you to do quantum research by simulating on, let's say, GPUs, accelerated computing.
Just to add to this, you know, those which are interested about quantum, we also have a special session in quantum during this Cyber Week. So please look on the agenda and register yourself also for this. And part of your question and more we will address in the quantum session. Additional question for NVIDIA. Yes, please. Mike here.
Thank you, sir. My name is Elio, and my question is about what is the way of getting access for startups to the latest models that you just described. Thank you.
So we release almost all our code. The research I described here actually does not involve a new model. You can take an existing model, like Stable Diffusion XL, things that are completely open source, and you can take our code and combine it with that, and we actually work to release efficient versions of our code and make it available to researchers. So this is actually pretty easy.
Okay, more questions from the audience? Yes, please, Mike here.
Thank you very much. My name is David. Do you think it is possible to combine diffusion models and large language models?
Yeah, so of course there's a large family of models called vision language model, right? Like LLMs, but now instead of just entering tokens that are words or text, you also add tokens that correspond to visual things. And so these are these models that you see outside that do kind of reasoning in multimodal text and images. But your question was more about generation of images, diffusion models. And there are several places where you can combine them, right? So today, the way you process the text, these text encoders are relatively simple. It's definitely possible that you can make the text part smarter to allow better control of the diffusion model. Another approach is today, there are a lot of ways to condition the diffusion models on more inputs that allow people to control better the image. For example, control net, right? So, for example, you can condition the diffusion models or like a layout, or structure of the image. And one natural approach would be to ask LLMs to generate layouts from text and use that to control some of the diffusion models. So there are a lot of ways to combine the two.
Okay. Thank you
you.
very much for Professor Gal Chechik.
Thank you.
Thank you. I need your clicker. Thank you very much.